Okay, so hopefully this is working. All right, today I want to talk about Zaino and the work I've been doing in the indexing department. So before we start, let's have a quick recap on what Zaino does and what's that about. So Zaino is part of the, let me see if there's actually something about documentation already. But Zaino is about replacing the existing Zcash stack and Light Wallet D. So currently, in Zcash, what you have is a full node. That will be Zcash D that we want to deprecate, and that's a full node, meaning that it's there to communicate with other peers, and it validates the blockchain. It provides security, etc., etc. But when you have a mobile wallet, you usually don't want to connect to a full node because the full node will you will download a lot of data. The blockchain is about 250 gigabytes at the moment. So that means downloading that much data to your phone in order to synchronize. That's that's quite a lot for a mobile device, and usually you want to do that. You want to communicate with a Light Wallet server. The Light Wallet server takes the full node, so it communicates with ZebraD, and it trims the blockchain into data that is needed for synchronization for your shielded wallet. But it doesn't have all the data, and the rest of the data you can query on demand. So most importantly, it doesn't have the proofs, and it doesn't have the memos. So all in all together, that represents a tenfold decrease in size. The compact blockchain is only 25 gigabytes. The main drawback is that it cannot be verified. Well, it's currently not verified by a proof, by a cryptographic proof. Therefore, you still have to trust the Light Wallet's server somewhat when you when you connect to it. But that's usually a compromise we're willing to take. So the current implementation of the Light Wallet protocol is called Light Wallet D. It's a project on GitHub, also under the same organization as Zcash, so the Zcash organization, and it's written in the Golang. As you can see, this is a Go project. Moving forward, now we want to deprecate Zcash, and we want to replace it with ZebraD or Zebra, which is fully written in Rust, contrary to Zcash, which is partially, well, a big chunk of it is in C++. And likewise, we want to go from LightWeight written in Go into something that is 100% written in Rust. So the equivalent for LightWeight would be Zaino. So Zaino GitHub is this project here. So this project is going on, and now let me describe what this guy does. So we already know that ZebraD would replace Zcash as a full node. Zaino is pretty much a replacement of Lightweight D, and it does three goals. He has three goals. One of them is it implements the Lightweight D protocol, right? So if you go here, and you go probably, I would say, in packages, yeah, proto. The interface is gRPC, so that's protobuf, and you have the definition of the service in protobuf. Lightweight protocol. If it goes here, right? So this is the guy, And what you see here in the actual gRPC definition, that there is a part about communicating and getting blockchain data. That's full blocks. So you can have a block ID. And this is stuff like that, getting raw transaction, getting balance, getting transaction history, or transaction again. So that's one part of tree state. So that's part of the API that is implemented by Zebra. So these are indexes are made on the full blockchain, giving you, for example, the balance at any given transparent address, UTXO history, and also the commitment tree hashes, stuff like that. That's done by Zebra. So that's one part. The second part is mempool updates. So you have, for example, this one, which gives you the content of the mempool, and either as a RPC where you ask for a particular transaction and you get the reply, or as a stream of notifications. So that's the second part. And finally, the last part, the last responsibility, and probably the most important for us here, is the serving of compact blocks. Actually, the interface is called Compact Transaction Streamer, which shows the importance of that last interface. So what we have here is, as I said earlier, Zebra has all the blocks, all the data from the blockchain. Zaino, or like what I did, will trim that to its bare essentials, and that's called a compact block. So a compact block is made of compact transactions. And the idea here is that the light wallet, like Zico, Zodo, whatever, will talk to Zeno and ask for a range of compact blocks instead of blocks. So again, this is like 10 times smaller than a regular block. And it goes through an API that is much more convenient than using the normal RPC on Zebra. So you can ask for a range of blocks starting from given height to end height, and you would give it as a stream. So progressively, you don't have to keep on calling. You open a stream, and then you will keep pushing the blocks to you. So the interfaces we really care about are this one. Anything that is actually has compact block in the signature is something that we have particular interest in. That's the role of the Zaino indexer, right? So there's already an implementation, and the work here is to make performance, stability, and testing improvements of that implementation. So the current implementation is in Zaino state, and the new implementation made is in there you go. Is here in repository. Where's the package is in Zaino store. So I have a bunch of stuff here. Most of these guys are I should move them to a tools directory properly because they are binaries and they are for administration and testing. So let me start with a demo. The demo is Zaino running. Well, we actually can start with Zaino from scratch. I use another server actually than this. This is a laptop. I prefer to go to a mini PC. which runs on Linux, which runs Linux. So this is Linux, and Zaino is here. Remote. See if that's the real one. It's the right one. Right, that points to my guy, yeah. And what else? I don't think there's anything that I need to pull. Okay. So I just need to make sure it's compiled. Okay. And then and the configuration of this guy is that there is it's exposed to the internet via HTTPS. So there is a reverse proxy. What did you do? It's over here. Okay, let's see nginx. Oh, it goes to sites available. Okay, so this is a conf, and as you can see, there's a gRPC proxy that goes from zaino-methyl.cc at port 9067 back to this guy here. So our service is running on localhost 9068, but from the internet you can use it from Zaino methyl cc on the classic gRPC port for light quality 9067. And here you have the certificate. So that means that our Zaino should be running with this configuration. So we're running with the fetch backend. Fetch backend just means that we are talking to Zebra using the Zebra RPC. This is where we store our database. We're connecting to mainnet. These two settings here, this is the concurrency. This is new. This is the concurrency factor. We form multiple threads for better performance, and that's a cap on how many threads we're using. And start height is whether you still ingesting from the genesis or you want to start at a later point. Sometimes it makes sense to start, for example, at sapling activation because you really don't have anything before for that point. And our port is 068 localhost. This is where the nginx will reverse proxy to us. This is the Zebra port 9232. This is the I think this is another RPC for Zebra. That's like a private internal RPC. So we're not really using this one. I think this one is for another way to ingest blocks. Okay, so what do we have? Now we have Zaino and Zebra running. So first things first, I'm gonna launch my client, pretty cool, and see that it's working fine connected to Zaino. So I'm using that mount Zaino, and I should see the height 3388701, which should match the current height. Yeah, 3388701. So this guy is running. I'm still seeing that everything seems okay for the feed. So if I stop that guy, if I go here and I stop Dino, stop one, then this guy shouldn't work anymore. Yeah, this error means that the nginx could not reverse proxy because the server is down. So it returns bad gateway 502. So at this point, we still have Zebra running. Our local Zebra is running on process as process 0, and you can see that it's still going fine. And we didn't stop it, and it's waiting for the next block. So what I'm going to do now is delete everything and assume that you want to start Zaino with a clean installation. As we saw earlier, the data is in cache, Zaino, and this is our block store. Normally, the block store thing should be inside mainnet. This is where the other guys are. I didn't move it yet. Let me actually just delete the block store. So that's a full delete. Well, I mean, full delete is a bit. Okay, let's move it. Okay, pretty much the same, but all right. So now, if we have that done that, and we restart Zaino, start one. What's gonna happen is, well, Zaino is gonna have to talk to Zebra and start getting the blockchain again because it lost all its data. And from the log, you can see that it's actually exactly doing that, right? It's going a bit too fast here, but basically these messages here are the ingestion. So it was oh yeah, it's going like 448 to 4, so that's 1000 blocks from this range to this range, 1000 blocks. It took half a second to fetch these from Zcash ZebraD. That's pretty fast because ZebraD is running on the same node as Zaino. So it only took half a second for these 1000 blocks. And our ingestion time is 572. So it only took 2 milliseconds to process these 1000 blocks. That's a speed of about 1.7 thousand blocks per second, which is fast but understandable because first of all we are on the same node, and second is there's nothing there, right? This is pre-sapling, so the blocks are essentially empty of any compact data. This is really blank stuff. But this is not. Yeah, 452 is before. It's before, just slightly after sapling activation. Kind of forgot. Anyway, now we are 600, and we are still running about 1.5 to 2000 blocks per second. So this is not bad, but we can do better than that. And we can do better than that because at this point here, we are so far behind the tip that we are sure the blockchain is never going to roll back that far. This is sometime in 2016. So it's impossible for the blockchain to have a reorg that deep. In actually, what we assume in the logic of Zebra and Zcash in general is that there's a maximum reorg depth. If we go more than, well, it's a configuration setting, but currently if we go more than 100 blocks, the validator would stop. And we take this assumption to say that anything that is deeper than 100 blocks, so earlier than tip minus 100, is finalized, is immutable, and we put it directly into our database. So this is what we call the freezer. All right, so this is going on, and it's gonna hit the spam phase pretty soon. At 1.7 million, we should see a massive slowdown. We're still actually quite far from that. So let me stop this for a moment. We stop one. Oh, one thing we can still see though is that as long as this is running, like we can restart it, and restart it obviously doesn't start it from the beginning. It starts it from let's stop it again. So start and then log. Yeah, so it continues at 800K, which means that if we are this guy here, and we decide, okay, we have to reset the birth to 420,000 and clear the data. Essentially, what I want to say is that this server is already operational. You can go here and click on this guy, and you can see that now it's responding to 459 because this was the height at which we were. So as it is eating blocks, easier to say, the server replies, and you can actually synchronize. Press this button, and this will synchronize blocks from this instance of Zaino. It works in quite okay in parallel. All right. Now in most of the time you don't want to do that. You have a faster path than that. If you use this path and you let it run until the tip, 3.3 million now, this is going to take you about 2 hours and a half, between 2 hours and 3 hours, depends on your machine speed and stuff like that. Um, so so what we gonna do instead is stop this and restart the same thing, but with the offline mode. So the offline or bootstrap mode. In this mode, we move Zaino block store. Okay, so now everything is gone again. We're back to nothing. In this mode, you can either run Zebra or you can stop Zebra. I think it doesn't really matter. I'm gonna stop Zebra just to be sure. But since we're reading offline, reading read only, I think it's actually fine to read to work online. Okay, so stopping Zebra now, and then I'm gonna use go back to the project. I'm gonna use the bootstrap command. The bootstrap is from Zaino admin. So admin is a new utility that some of the stuff that I added to manage this new indexing. So we bootstrap. We provide the configuration file, and I think there's one parameter missing, which is the path to the Zebra database. So Zebra database was cache Zebra, yeah, cache Zebra here. Then this guy reads the door, and off we go. Right, we are now connected to. It's scrolling too fast. It's connecting to Zebra, and it saw that the tip is at 3.3 million, and it's eating these blocks. So you can see it goes faster, much faster. We're already at 600K, 700K. Then that's 30% now. It's gonna go. This is gonna crawl to a halt at 1.7 million because that's where the spam begins. So let's not be too excited about the speed here. That's not going to last. Okay, bang! Now we are scrolling. All right, so this gives me some time to talk about this, how this is done, design of this stuff. All right, so we're gonna put this aside and go to the code. So the code that we need. So this is just going to be an overview of the code. All right, so we have We have a few things. The first commit was fairly mechanical. It was about let's talk about the structure of this stuff. So you have this is the new stuff. This is the admin command. Again, that shouldn't be here. We have this check command, which connects to takes two server URLs. So typically you connect to your Zaino and you connect to either another Zaino or you connect to library. So the other one is like a reference server. Then you give a block range and it's going to issue get range requests on both servers, get the blocks and compare them. So the compact blocks should be equal if your code is correct. So this is like reference sanity reference check. Oh no, sorry. This is compare. Compare does that. Check is different. Check gives you take gives a range, and then you download these blocks and make sure that the blocks are chained properly. So one of the challenge of this this app is that the blockchain keeps changing. You if you do a scan from 0 to 3 million, it's gonna take you hours, and it's very obviously the blockchain is gonna change in that time. So if you get a request that comes and request from blocks while you are catching up or synchronizing, there's a chance that, or the chance is higher the longer the range is, that there's a chance that the blockchain updates during your request. And it can update in two ways. It can update by extending the tip because one block comes just normally after the current block, the latest block, and makes the blockchain grow larger by one just at the tip. But there's also a chance that the update you get from Zebra is a fork. So it's a block that does not extend the tip but connects somewhere before. In that case, the data that was returned to the client, if you're not careful, will not be consistent because you are essentially saying that the blockchain has changed. Blocks that were served before may not be connected to the blockchain anymore. Right? So if, for example, you do 1, 2, 3, 4, 5, and then the new block comes, but instead of being 6, it's actually an update on 2, then it means that the blocks 3, 4, 5 that you have maybe sent are not the latest blockchain anymore. So we don't guarantee that. What the guarantee that we are giving is that the stream that you are sending and that you're receiving on the client is consistent. It's a snapshot of the blockchain at the moment it was made. So you will see 1, 2, 3, 4, 5 on the old chain, and the assumption here is that the wallet later would retry, would also call for an update of the blockchain. Then it will see it will think that it has already 1, 2, 3 to 5, and then it will ask for block number 6. But the block number 6 that it would get would no longer be following the block number 5 that it got earlier because there was a reorg. And because of the mismatch of previous hash, the wallet would notice that this is a reorg, and it will request the blockchain again at the earlier time. So the main guarantee though for Zaino, and I'm not sure actually that library enforces that, but I really think it should, is that whenever you get a range, you get a compact range, the compact range is guaranteed to be consistent, that it represents a blockchain at a certain moment of time. And that moment of time, the blockchain was the best chain, and all the blocks that you get, even though they are maybe no longer valid, no longer the best, the block that you get are correctly linked from previous hash to previous hash. So this is exactly what Zaino check does. Zaino check will issue a ton of, not a ton, but it will issue uh, a get range request starting from the given height and up to the end height. If you don't say anything, it would go to the tip, and it will show you how long it takes, and if there is any inconsistency with the chain. So obviously you don't want errors to be, there should be any error. This is the inner check, very fast consistency or correctness check. Then you have Zeno concurrent test. This one is a client load test. It's gonna create, I think, up to like thousands and thousands of it's a parameter. It's you give a range, and you give a number of concurrent clients. So it's gonna spawn like say 5,000 clients, and all these clients will request a different range of blocks. So the blocks will not if you give a range that's large enough, all these clients will request different ranges, and then it tests that the server, they know, is capable of handling that many connections, and also that many connections on different ranges will not create performance issues. Because it's one thing to handle like 5,000 connections. It's another thing to handle 5,000 connections, each of them asking for a different part of the blockchain. So this is what it has. This is a quite difficult test. It's pretty strenuous, but we're doing pretty fine. Maybe we can run it later. Then you have gRPC test. This is just a functional test that with this change, the gRPC API, all the methods of the gRPC API are still working. So obviously this is just supposed to change the indexer, but we don't want to. So we don't want to touch the mempool, and we don't want to touch the transparent and full block API. So this test here will make sure that we are still can call the client can still call the other APIs. It's not broken. So these are actually high top level binaries. So I think I should move them somewhere else. But the real packages are common. So common are common utilities. Fetch is the stuff that knows how to talk to Zebra. Then you have proto is the gRPC protobuf stuff. Serve is the server. Zaino is a server, obviously. And then you have these two guys here. So state is the current implementation of the indexer, and store is the updated one. So what you have in state is this main guy is chain index. So before chain index was basically doing everything. Every method that goes through the gRPC will eventually delegate to chain index. So one of the thing that I've done early was to split that into these three responsibilities: the mempool, the Zebra forwarder, and then the indexer. So the main reason it was to have better code separation, so that if I change the if I implement a new indexer, I just have to implement the indexer trait. I don't have to do the full chain index. And then the implementation just simply aggregate three of them, and then has blah blah dot mempool, blah blah dot indexer, blah blah dot what's the last one? zebra, something like that. Right? So we are just forwarding to the proper subcomponent that does the implementation of the particular role. So that means that we have somewhere replaced the zebra state with the Zaino, not zebra state, Zaino state with the Zaino store. So Zaino store here is where we are have our stuff. We have let me see, forgot already. State here. Okay, let's see how far we went for this guy. Well, we're still in the spam zone. So we made some progress. We this is on my timer. Once this is done, we stop talking. Okay, so the model here is it's very similar to what we had before actually. We have our state is the most basic stuff that we do is this block, notional block. And the notional block is simply something that has a height, which is integer, which is the index of the block from 0. So the genesis is 0. And that guy has a hash, and it has a reference to the previous block, so previous block hash. And then you have some data here, but the data is opaque. So this whole Zaino store doesn't really care about what the blocks are. So that keeps us agnostic of the actual implementation of the compact block. So for the purpose of blockchain and indexing, we don't care about that. What we know is that a block has a height and it has a previous hash. It also has a hash, of course, right? But we actually don't need a hash. I mean, we are going to be past the hash, but we don't really need the hash we don't need to store the hash. Then we have this notion of block, and then we have the notion that block is part of a chain. So you take a block and then you look at the previous hash, and that gives you another block. And if all the blocks that you have are linked like that from their previous hash, we call this a chain. Right? And if the chain all goes all the way to the beginning, all the way to the genesis, this forms a fork. Right? So the purpose of this code here is simply to manage forks. Right? And the trickiness, of course, comes from the fact that you have the chain, the forks, they updates in real time coming from Zebra. Zaino does not really control that. Zebra doesn't control that either. It's all coming from mining and transactions that are outside. So what we want is to have some kind of replication system where Zaino replicates what Zebra thinks is the best chain, the best fork. So Zaino doesn't also care about how best chain is decided. That's a validation, and this is a consensus rule that comes from Zebra. All Zaino does, is to deal with getting to the client a consistent chain or blocks. And when a client asks for a new chain, the current chain, that chain should be its best knowledge of the current chain. Right? So there's always a delay because Zaino is not going to be 100% aware of Zebra updates, but there should be some convergence. Right? The Zaino should update based on what Zebra thinks is the best chain. And likewise, Zebra actually cannot know, because it's a distributed system, what is the best chain. It has also its notion of what is currently best, but it should converge to the same thing. So for us, this best chain is represented as this guy, right? Is represented as actually two parts. We represented as a map between block hashes and blocks. Right? This is our PHM, and PHM stands for persistent hash map. So this is a hash map. Persistent is maybe a bit misleading but this is the terminology for functional programming languages. So it just means that this hash map is immutable. It's still in memory. So if you stop the program, this hash map goes away. So this hash map contains mapping between hashes to blocks for the latest 100 blocks. So this is in our non-finalized zone. This is our transient phase where we think that there could be reorgs and there could be change of best chain. Therefore, that hash map is not written to disk. And then there's stuff before, that's our freezer, our LMDB database, which stores anything that has an age older than 100 blocks. And based on the assumption that we cannot reorg more than 100 blocks, it means that everything that goes to LMDB is immutable. It's not going to change. So LMDB is going to be a map of height to blocks. Right, so there's a difference here between the PHM, which is a map between hashes and blocks. The hashes to blocks is always stable. The blocks cannot change, therefore the hash cannot change. Therefore, a hash to block is going to be a pure function. But a height to block is not a pure function, because you could have a reorg that changes the block at a particular height. But since we say that you cannot have that happening deeper than 100 blocks, anything that is older than that threshold is as good as analyzed. Therefore, for these blocks, the older ones, the height to block is a pure function, and then we can store it like that. So the difference here is a bit subtle, but it allows us to get the freezer very quickly, because when you ask for a range, anything that goes into the freezer range is going to be read directly from the database using a height. Right? And the same thing when we do the bootstrap, what we do is we actually inserting directly into that LMDB. We are bypassing all the logic about maintaining branches, maintaining forks and chains. Go straight to the database because we know these guys are permanent. Okay, and then so the freezer here is basically our archive. Right? It's like when you read your emails, anything that is old, you can put it to the archive. And of course, when the client asks for a range that isn't passed, you're gonna use your freezer, but you're never gonna rewrite your freezer. So the interesting thing is actually what you do in the PHM, in the non-finalized part. And then here, essentially, we have two things to do. One thing is we're planning to request that ask you for a range that overlaps the non-finalized zone, and how to deal with adding blocks to it. And this once you cover these two, you're basically done. Right? So what we do here, let me see if it's down here. Okay, we don't have too much time. What we do here is that, so I'm gonna speed up here. So what we do here is that we use data structures that are immutable in the sense that when you add something to the PHM, the old PHM is still valid. So if you have the PHM is basically a tree, right? And when you add a node to the tree, if you have a reference to the old tree, you still can use it as it was. You're not mutating the hash map. So if you have a reference to the old hash map, you're gonna see it's basically a snapshot of what you had before. So semantically, it's as if and whenever you add something to the PHM, you were cloning everything. You would have a new copy of the PHM with all the old blocks and your new one. But obviously, this is not a full in-depth clone. The PHM, when you add something, or well, actually, it's only adding is the only thing that we use, is essentially a all log-n operation. And there are no copies of blocks anywhere. So this whole thing is actually done in like in nanoseconds. So uh, it's 01 for the blocks. Nothing is really copied. There's no deep copy or anything. Some reference counters are updated, and but from the semantic point of view, you cannot see anything that is in a transient state because logically what you get when you operate on the chain state is a copy. And again, this is not a real copy, it's not a materialized physical copy, it's just a logical copy. So this guarantees us that whenever we take a snapshot and we turn a chain to the client, this is a chain that is going to remain valid even if there's a reorg that happens in flight. So all the stuff that you have here, data structures are like that. Right? Again, they appear to be deep copies, but no, they are just structural copies that share a lot of state from the previous stuff. Right? And what you have here is basically our view, the client's view or Zaino's view of the blockchain. Right? So blocks is a map of everything that we know over the last 100 blocks. So everything that we have received as a map from block hash to block. Then we have a height, which is is a vector of hashes for the current best chain. So for example, you are at height 3 million. So 3 million will point to a particular hash, 3,000,001 will point to another hash, and so on and so forth. So that vector will just be the vector of these hashes. Since the blockchain cannot have holes, we can store it as a vector, just keeping track of the offsets to the first element, the height of the first element. And this is implied because we know the tip. So we have the tip, and then you have this guy here, and this guy here is when we do the freezing operation. So you see that this chain state is going to change a lot. Every time you receive a block, the new blocks will enter the chain state at the end as the latest block. But since we know that we have a limit of 100 blocks before they are mature, the oldest one matures, we can trim that chain state. We remove the one that now is older than 100, now is that 101, and we remove all the blocks that were considered at that height. So there may be more than one, because while we're doing all this stuff, if there are reorgs, there could be blocks that are orphaned, but were at a height that is now frozen. Right, so we have this height to hashes to keep track of the stuff that we basically can garbage collect. And when we garbage collect, we only have to pick one of the guys from that height to store in the freezer. All the rest that are orphaned, we can then throw away, and that frees memory. So this data structure here is basically 100 blocks plus the ones that orphan due to reorg. That's not a lot. Then you have the logic here to manipulate this guy. So we can look, we don't have time to go into too much details because, well, the stuff is complete. So it took us 52 and it started at 31. So that's 21 minutes. Okay, so after 21 minutes, our freezer is complete. This has not written the PHM. The PHM is in memory data structure, so the last 100 blocks are not persisted since they can be reorged. But that's good enough because we got 3 million and 3.3 million blocks. And now we just need to restart Zaino. And Zaino can now pick up. Oh, I have to start Zebra first. Okay, let's see Zebra. Be a connection fail. Oh well, hopefully. Oh no, this is still. I think still opening the database. So at this point, actually, see, I think Zaino retries automatically. Yeah. So Zaino connected to Zebra and processed the little like leftover it had. It had of course always 100 blocks to download because that finalized non-finalized zone is never persisted. But it may have a couple of blocks because we waited. But all in all, the catch up only took us 3 seconds. 3 seconds to do that part. So the initial sync, it's not really initial, but it's 3 seconds. And now we are up to date. So if we go to the goal and we press this button, we are 3388724. We should be 7 to 6. Well, we're a bit behind. Must be our Zebra and not completely up to date. Oh yeah, it's not up to date because I just restarted Zebra. All right. Anyway, let's see if we can do one transaction. So the real test is I should synchronize this guy first. So this is way too early. We put back to 3 million. Then we set the state and do a synchronization from 3 million. 3 million to tip. That's about 300,000 blocks. That should take us a few seconds. So this test is good because it shows that we managed to use ingestion from ZebraD database of that range, and that all the blocks are linked properly. Otherwise, the wallet would detect a break and stop at that point. So we now can be sure that the chain that we are getting from Zaino is correct, at least correctly linked. And the last test is if it's really correctly linked and all the data is correct, then we can make a transaction. Right. So I'm going to make a transaction to myself for the full amount. I only have that much. And okay, so just a orchard to orchard transaction for testing. All right, so that was transferred, and we have 0D35. If we go to here, we should see our transaction in the main pool. Yeah. Where transaction main pools? Oh, here, main pool. Oh, how does it work? 0D. So this is us, and this is shielded to orchard to orchard. So now we know that Zaino has indexed properly and is at the tip. All right, that's it. Okay. So this is essentially how the rewrite works. There are a couple of things that are interesting here. Say is the logic of how to do ingestion, how to add, how to work with the freezing and stuff. But it would be detailed in the PR. Another thing is there's the model for this is in Lean. You can we go here, and there's a proof that a pretty big proof that this logic here is correct. So we have all the invariants, pretty variable stuff. It checks correctness of the chain membership theorems and what happens when you insert a block and all this stuff. Yeah. The Lean code is actually way more complex than the Rust code, and I think that if you read it from the Rust or design paper document, it's not that complicated really. All right, but that's it for now. Yeah. Okay. See you later.